Okay, we are going to look at autotransformers, both step up and step down. So here we have a picture of a mutual induction transformer. And you see on the mutual induction transformer, there is zero connection electrically between the primary and the secondary. Um, but over here on the autotransformer, it's a little bit different. You see that we have only 3 terminals for connections, and it is electrically connected. All right, so we have no isolation from the primary circuit for our output there. So that's one of the major differences between a mutual induction transformer and an auto transformer. It uses self-induction to operate. Here's a picture of a step-up auto transformer. And so in this case, we'd have our lower voltage coming in. We could say it's 120 or something like that. And we'd put out a voltage of, let's say, 240, something like that, or better. All right. So to look at this, we have to say we're going to identify parts of this auto transformer. So one is the series winding. So on a step-up auto transformer, the series winding is the one that is in series with the load. Okay. And so the series winding in a step-up transforms in series with the load, whereas we have the other part of this winding is the common winding, and it is common with the supply or the source. Okay. If we look at a step-down auto transformer, we have both the series and common winding, but this time in a step-down, the series winding is in series with the supply or the source, and the common winding is going to be as common to the load. So whatever voltage is on the common winding is going to be the same as the load voltage. Okay, so the voltage relationship in a step-up auto transformer. So because both windings are wound on the same core, they still have the same volts per turn for each winding. So let's say that in this step-up auto transformer, we had a 240 volt source. And in the common winding, so from here to here, there was a total of 480 turns. We could figure out the volts per turn. So 240 divided by 480 turns gives us half a volt for every 1 turn. Well, that same half a volt per 1 turn is what's on the series winding here too. Okay, so whatever it is established there is what it's going to be as well on the series winding. So if I had 120 turns on the series winding and total combined 600 turns, we could determine the voltages. So 120 turns times 0.5 of a volt per turn, that gives you 60 volts. And if we add these two voltages, 240 plus 60, that's going to give us 300 volts. Or we could look at 600 turns times half a volt per turn. Total is also 300 volts. All right. So 300 volts. And here's the voltage relationship on a step down. Once again, the volts per turn ratio is going to be the same. So here's a 600 volt source, and the total turns of both series and the common winding combined is 2400. So our volts per turn would be 600 divided by 240 turns. That would come to 0.25 volts for every 1 turn. Okay, the turns on the common winding, if we had 1,920 turns, so 1920 times 0.25 volts per turn. Okay, what would that give us? That'd give us 480 volts. So 1920 turns times a quarter volt for every turn gives us 480. And we could figure out the voltage of the series winding too if you wanted to. 480 times 0.25, so that'd be what, 120 volts per turn, or 120 volts on the series winding. Okay, looking at the current relationship. So what happens with this is, well, the number one rule still applies for transformers. Whatever the volt amp output is going to be whatever the volt amp input is. Okay, and so we're going to use that concept when we're looking at this. We're going to calculate the VA of the load, and we know that that's going to be the VA coming in. And if we know the VA, we can figure out the current coming into the transformer and the current going out of the transformer. And then we can determine how much current is through the series windings and how much through the common windings. So the secondary voltage is lower than the primary voltage. So you know that the secondary current has to be the higher value because VAN equals VA out. Same thing when we're looking at the step up autotransformer. All right, if we know the VA output, that's going to be equal to the VA input. So we can use that VA load that this transformer is under on both the primary and secondary, calculate the current coming in in the source and returning, and then calculate the current going out to the load and returning. And from then, we'll balance it out, and we can see how much current's on the series and how much is going to be on the common winding. So let's give you an example with this and start working with this. So in this example, we have a step-up autotransformer, and our supply voltage is going to be series winding, common winding. Yep, identify them. The series step up, the series windings in series with the load. The common winding is common to the supply. So we've got a 240 volt supply, and it's going to step up. This autotransformer is going to step it up to 600 volts for a 600 volt load, and this load is going to draw 12 amps. All right. So the number one rule was VA in equals VA out. So on this one, we can calculate the VA output, or the S output, is going to be equal to 600 volt times 12 amp. And so that brings us to 7200 VA. So 7200 VA. Well, whatever the output is the same as the input. So if I bring that VA to the front, we've got 7200 VA coming in. And I can then go ahead and use my VAs, my voltage, to calculate the I of the primary. And I can also use it to, we've already got the I of the secondary. It's 12 amp. So the I of the primary, we'd take 7200 and divide it by 240 volts. And that comes to 30 amps. So we got 30 amps coming in right here. And whatever comes in has to go back, 30 amps. All right. If we look at the load here, the load draws 12 amps. So current comes out always on the top, 12 amps. And it comes back, 12 amps. So if we use Kirchhoff's current law here, the series winding in this case is going to be exactly the same as the secondary current because there's only one path here. So we got 12 amps going through the series winding. So if we got 12 going up, we've got 30 coming in. What's the difference between the two? So that would be 18 amps. And we have to have 18 amps flowing away from this junction, going down. So what would be our I of our common winding? Would be 18 amps. All right. And does that add up on this junction? Sure. 18 comes in plus 12 coming in, 30 leaves. Perfect. All right. So there you go. So that's how we could calculate how much current is going through each winding. Now we're gonna give you a couple more formulas here. It's the conducted VA and the transform VA. So we can look at how to calculate transform VA and conducted VA. So the transform VA is equal to the voltage of the common times the I of the common. So in our case, the voltage of the common is the supply voltage because we're using a step up. So that's 240 volts. The I of the common, we calculate it with Kirchhoff's current law, 18 amps. And that gives us 4,320 VA. The conducted VA is voltage of the common. So both of these formulas, step up, step down, doesn't matter, doesn't change, is voltage of the common. Okay? So that's 240 volts times the I of the series, which is 12 amps. We calculated that right here. So 240 times 12, 2,880 VA. So if I add those two up, it comes to 7200 VA. So we can figure out how much of this load is transformed and how much of it is conducted. All right, so the total 7200 VA. It's exactly what we come up with when we first initially looked at it. Let's have a look at a step-down transformer. So in this scenario, we've got our supply and our load, and this time we'll identify our windings. Our series winding on our step-down transformer is in series with the source or the supply. And the common winding, well, its voltage is the same voltage the load sees, so it's common to the load this time. All right, so our supply is 480 volts. Looks like our load is 5000 VA. All right, so we're going to do exactly what we did last time. We're going to determine the current in each wire. So if I have a 5000 VA load, VA output is the same as VA input. So the current of the secondary, we take 5000 divided by 120, it's 41.67 amps. So that means out of this junction, 41.67 amps flows to the load, and it's got a return back right here. Okay. Now if we calculate the primary current, 5000 VA divided by 480 volts, we're going to have 10.417 amps coming in. So comes in, there's only one path, and it's to go through this winding right here, which is our series winding. So that ends up being the I of the series. And then, so that 10.417 comes down, 41.7 splits, takes off, 41.67 comes back, so we have to have current coming back to that junction. Goes in, and then 41.67 leaves. And 10.417 has to return. So this conductor has to be the same current as this one coming back. So what's the difference between 41.67 and 10.417? The difference between is going to be 31.25. So looking at this junction, 10.417 comes in, 31.25's got to come up, and 41.67's got to leave. So that one works out. Check a look at this one. That 41.67 returns from the load. 10.417 continues back to the supply. So the 31.25 difference has got to also leave and go back up. So that's how we can use Kirchhoff's current law. Once again, we can do the conducted and transformed VA. Transform VA, V common times I common. So the common winding voltage is 120. The common current, we calculated it at 31.25. So we multiply 120 times 31.25, we've got 3,750 VA. The conducted VA, via the common times I of the series, so the common voltage, once again, 120. The current in the series winding, we figured out to be 10.417. And 120 times 10.417, 1,250 VA. We add up those two VAs, and it should be our original 5,000, and it is. Okay, let's have a look here. What autotransformer, some advantages and disadvantages of them. So first we're going to go over some advantages. They're ideal for small voltage changes. So a variac is an example of, or is an example of a, is how we can adjust voltages. And so we use those variacs in our lab bench for variable voltage supplies. They're smaller and cheaper than a mutual induction transformer to get that same output voltage. They have a better percent voltage regulation, so that means that from no load to full load, their voltage will not change much. And increase kVA capacity. So if we take a mutual induction transformer, we could reconnect that mutual induction transformer and use it as an autotransformer. So we're going to have an example of that here. Here is a mutual induction autotransformer. Its kVA rating, when used as a mutual induction transformer, is 3000 VA, or 3 kVA. So it's right now the primary voltage, so we're using it as it's drawn as a step up here. So the X winding has a 240 volt rating and 3 kVA, so we could calculate the rating of the primary here if we wanted. Okay, that would be 3000 VA divided by 240 gives us 12.5. The rating of the secondary, 3000 VA divided by 480 is 6.25. So that's its normal input current, and so current on the primary, and its normal current on its secondary. So I'm going to reconnect this now as a mutual induction transformer. Remember, these ratings are the maximum current flow through each individual winding, so it won't cause it to overheat. So as long as we don't exceed the voltage on each winding, its rating, or the current flow to it, we're okay. All right, we're going to be fine. It will not overheat. So here's what this looks like. If I reconnect it, there's our new 3 terminals that you would see in an autotransformer. Now, it doesn't look much like our autotransformer that we drew earlier. So I'm going to take this same picture. So if you notice, line 1 comes into X1 here. Okay, X2 jumpers to H1 over here. And then we have H2. So I'm going to reconnect it. So this next slide here is that exact same transformer, how we could see it. So we've actually made a step-up autotransformer. Let's have a look before we continue. We're going to put our 240 volt, okay, between X1 and X2. All right. And then in this case, we've got H1 is connected up to X2. So it's in series with the X winding. And we're going to connect our load between H2 and X1, right? So we've made a step-up autotransformer. So let's have a look here at these rated values, okay? This is step up, so the series winding is in series with the load. The common winding is common with the supply voltage. It has a rated current, so the I of the series winding, the maximum is 6.25 amps. The I of the common winding rating is 12.5 amps. Now, just as we did earlier, if we use our conducted and transformed VA, we can calculate what this new VA rating of this transformer is going to be. It's not going to stay at 3000. All right. So the transformed VA is going to be equal to the V of the common times the I of the common. So 240 volt times 12.5 amps. There's our 3000 original VA. But then to this, we're going to add the conducted VA. So the conducted VA is V of the common times the I of the series. So that is 240 volts, voltage of your common, times your I of your series, which is 6.25 amps. So we're getting an extra 1500 VA out of this transformer when we connect it up as an auto transformer. So the total is 4500 VA, so 4500 VA. And we are producing 720 volts. All right. So calculating the new VA rating if we use a mutual induction transformer reconnected to an auto transformer. This is the example of that. So some disadvantages now of an auto transformer is they do not isolate primary and secondary circuits. So where we need isolation, you cannot achieve that with an auto transformer. They have a lower percent IZ rating. So what does that mean? They're going to have a higher short circuit current availability. And in a step-down auto transformer, the supply voltage could be applied to the load if we have some sort of fault in our transformer. So I've got a little diagram what that fault might look like. So we're trucking along here, and we've got your series winding, your common winding, and so we got a 120 volt load and a 40 volt supply. All of a sudden, whammo, okay? For some reason, we get an open on this common right here, okay? The common opens up. So if that happens, now we could see as much as 480 volts across our 120 volt load over here. So that voltage could rise to the supply voltage just about. So that could be quite hazardous for the load, could make it burn up. So that's about it. So Autotransformers. Hopefully this helps you out. We'll see you on the next video.